hope you're not too tired. I am a bit, sorry. So my name is Timothé Krauth. I'm at the very end of my PhD here. It has been supervised by the Zurich University of Applied Sciences and the ONERA in France. And I'll try to talk to you about a summary of my work over the past 3 years, which is called Deep Generative Modeling for Mid-Air Collision Probability Estimation. This is a bit complex title to actually say very simple things. First of all, let's talk a bit about some context here. So at Zurich Airport, there is kind of a problem that is called the GATO 1416, which states that when an aircraft is arriving on runway 14 in blue here and misses its approach, its go-around trajectory intersects directly the departing trajectory from runway 16. So it's not very efficient for the collision risk here. So to mitigate the collision risk, stakeholders at Zurich Airport have introduced this cutoff distance where when there is an aircraft in this distance, no aircraft can move from runway 16. So this is very efficient to mitigate the risk of collision, but this is not very efficient for the capacity of the airport because you have quite a lot of aircraft arriving on runway 14. So you can see here some plotted of observed takeoffs and go-around trajectories on the right. And you can clearly see that, yes, they are quite intersecting. So the goal here is that can we try to quantify actually the risk of collision induced by the design of those procedures here without the interaction of ATC, only the design of the procedures. So if we want to estimate the risk of collision, of course, we need a collision risk models. And I'm not the first one to try to do that. It exists quite a lot of collision risk models in the literature, as then can be divided into two main groups. The first one is what I call the geometry-based models. Those are models that are making a lot of assumption on the trajectories themselves with well-structured aircraft flows. So basically, trajectories that are flying with constant altitude, constant speed. And we also have some uncertainties on the position, on the speed as well, that are modeled with chosen density distribution. So we have a lot of assumption with those geometry-based models. And they are very, very efficient for en route collision risk models, so basically across the ocean, for instance. But they lack flexibilities if we want to apply them in terminal maneuvering areas, so basically airspace around the airport, because you have a lot of altitude changes, heading changes, and the trajectories are way more complex. Alternatively, we have what I call the Monte Carlo-based collision risk models, which are based on Monte Carlo simulations. Those are very simple, actually, to use. We just simulate a pair of trajectory that is following the procedures we want to assess, and we count the number of times we observe a collision. We don't make any assumption. It is adaptable to very diverse scenarios, but they are quite difficult to apply if we want to estimate a very low probability of collision, because we need to have actually a lot of simulations of pairs of trajectories. And we don't necessarily have the data to perform such big simulations. So the idea I had for my PhD is to use those Monte Carlo simulations with a generator of synthetic aircraft trajectories so that I can simulate millions of pairs of trajectory quite easily. So how can we try to generate synthetic aircraft trajectories? So to do that, I have used a variational autoencoder, which is a deep generative model to estimate the distribution of the observed trajectory and to try to reproduce it by generating new trajectories. So to be fairly simple about the architecture of a variational autoencoder, it is composed of three main components. The first one is the encoder. The encoder is a neural network that takes as inputs an input trajectory that we have observed in our training data set and encode it into a posterior distribution. So you have to be aware that we have as many posterior distribution as we have input trajectory, because each input trajectory is associated with a different posterior distribution. The second part of my variational autoencoder is the latent space. The latent space is the representation space where are living all of those posterior distribution. And the main goal of the variational autoencoder is to make those set of posterior distribution, the mixture of posterior distribution, as close as possible to a prior distribution that we have chosen before. And finally, we have the third part of the variational autoencoder, which is the decoder. The decoder simply takes an input that has been sampled within the latent space and decoded back into a trajectory. So if I take an input for the decoder from the posterior distribution, I will reconstruct an observed trajectory. But if I take an input from the prior distribution, I will generate a completely new trajectory. This is my generative distribution. And this is what I did actually here. So on the left, we have the latent space, or the two-dimensional representation of the latent space, and I have generated into two specific components of my prior distribution. I have decoded those sample points, and you have on the right some synthetically generated trajectories for two very different regions of my latent space. So we have two very different behaviors of generated trajectories. So those are the lateral shapes, and those are the altitude and the ground speed profiles. So when we look at that, we say, okay, it looks cool, but we have to assess the quality of the generated trajectories. Are they good or not? So to do that, I have used two different statistics here. The first one is I want to assess the statistical realism. Is the distribution of my synthetically generated trajectories close to the distribution of the trajectories I have observed in reality? To perform that, I will use what is called the energy distance. The energy distance is a metric that assesses the difference between the distribution of two samples. And I want to apply this energy distance between a sample of observed trajectory and a sample of generated trajectories. I have compared different estimation methods, different methods to generate synthetic trajectories, one Gaussian mixture, and different architectures of variational autoencoders. And the architectures I'm proposing in one of my papers, in the last one, the temporal, convolutional, and prior variational autoencoder. Yeah, that's a bit long. But what you can see here is that the E distance for my proposed architectures is the lowest. So it means that statistically speaking, the variational autoencoder is able to build the synthetic trajectories that are the closest to the reality. The second point I want to assess is that are the trajectories I'm generating flyable by an aircraft? That's a question we can ask, because in my variational autoencoder, I don't have any insight about the physics behind those trajectories. To perform that, I have used an aircraft performance model. So this is basically a model that takes as input some waypoints. It is based on flight dynamic equations and gives as output a trajectory that goes through those waypoints. The very simple idea I had is if I'm taking a synthetic trajectory and give it to my aircraft performance model, the output of this aircraft performance model should be very close to the synthetic trajectory I have given as input. So this is what I'm measuring here. I'm measuring the distance between the input, so the synthetic trajectories, and the reconstructed counterpart through the aircraft performance model. So once again, our model here, the one prior to CVAE in orange, is the closest to the reference, which is the metric applied to the reference. And the reference is the observed trajectories. So yeah, we know how to generate trajectories, and it looks like it works pretty well with the variational autoencoder. But this is not sufficient to estimate actually a risk of collision here. I tried to do that last summer. It didn't work very well. So we have to have some further considerations, further improvements of these variational autoencoder architectures to make it fit our trajectory, our prediction, collision estimation problem here. So I want to introduce here disentanglement in the variational autoencoder. So disentanglement, it's a bit complex tool in the field of deep generative modeling and representation learning. But I found one cool definition in one of the papers I've read here. So this is a latent representation where a change in one dimension corresponds to a change in one factor of variation, while being relatively invariant to changes in other factors. So in other terms, disentanglement means that I should be able to build a latent space in my variational autoencoder where one dimension corresponds to one physical characteristic of the trajectory I'm generating. So that when I want to choose which characteristic of my trajectory I want to modify, I just have to modify one specific dimension in my latent space while keeping the other component of the vector constant. This is super hard to achieve, actually. But in all of the papers I've read, it can be achieved by choosing a factorized generative distribution. So for my prior distribution, I have to have a specific shape of this distribution with independent marginals, so that the distribution of the observed trajectories within my latent space are factorized as well. And then I apply some regularization in the training of my variational autoencoder, and let's see what we have as an output of these disentanglement features. So I have trained one variation autoencoder to generate this time a pair of trajectory from one model here. So we have my training data set on the left. So pairs of takeoff and go arounds for Zurich Airport. And on the right, we have the distribution of each of the distribution I have in my latent space on each of the dimensions. So we can see that some of the dimensions are meaningful when we vary them, when we see the influence on the generated pairs of trajectories. And what is super interesting here is specifically the fifth dimension here. The fifth dimension in my latent space is distributed with a two-mode distribution, and each of those two modes is corresponding to the direction of the generating takeoff of my pairs of trajectories. So if I go back to the beginning when I present this Gato 1416 problem, this is pretty nice because by only choosing where I'm placing the cursor in the fifth dimension of my latent space while keeping the other dimension completely random, I'm able to generate a pair of trajectory either for the takeoff either going west or going east. And this is super nice because actually the risk of collision is very different for the eastbound departure and for the westbound departure. So yeah, now I've presented how I managed to generate more trajectories. I don't have the time to present you into details how I estimated a risk of collision, but if you want more details, I'm defending my PhD next week, actually. So I can share the Zoom link if you want. I will be happy for if you want to participate. Yeah. Sure, question?
Much. A lot of questions over there, maybe.
Well, you know, I am following your work, and I just want to congratulate you publicly for what you are doing because it's very interesting. I just ask one question, and it's who is going to be the client of your model and for what purpose? And just good luck with your PhD defense next week.
Yeah. The client, as it has been discussed over, I guess, almost all the presentation this afternoon, there is quite a gap between the academic research and the client in the end, because it's super hard to sell it actually to air traffic controllers. Say that, okay, we have a fancy model when we generate aircraft trajectories, but if they look at those trajectories, they say that, yeah, no, it never happens in reality. So yeah, it's not very, it's not very realistic, etc. But ideally, we would like to sell it to, for instance, or sell it, like, to provide it to Zurich Airport, for instance, so they can try by trying to determine the influence of this cutoff distance between runway 14 on the risk of collision. This is what they want to do, actually. How much I can reduce this cutoff distance here before the risk of collision induced by the design of the procedure becomes too great. So that's what it should be able to do at the very end of the work. So if you have any, yeah. So
Thank you very much for your presentation. I have a question regarding the feasibility of changing the direction of the plane once it departed. So knowing that there will be some communication between the air traffic controller and the aircraft, once you know that the plane that is arriving missed its approach, did you take into account the time for communication and?
No, not at all. Here, we don't generate synthetic trajectories sequentially. It means that we generate the whole trajectory at once. So they doesn't change anything. What we wanted to do here is just to have a look at are the procedures dangerous or not if they were flown completely independently. So imagine that we have a lot of aircraft that are departing or arriving completely independently. Do we have a risk of collision? And this is actually a bit hard to understand because that's not what we observe in reality. So we have to build it from scratch to measure this influence of this risk induced by the design of these procedures. And then after that, if I want to go until the very end of the estimation process, until the reality, I have to take into account, of course, the communication time, the failure probability of air traffic controllers, etc. And so this becomes also way more complex as well. But here we only focus on the design of the procedures.
Hi. Thank you so much for the good presentation. I think I have read your work.
Nice.
It's a good paper. collaborate with Xavier, right?
Yeah, Xavier is my
Yeah.
PhD advisor.
And I have two like small questions. So the first one would be, have you tried like GAN? So it's like a different structure, like model structure with VAE. So
Not necessarily. We actually, of course, at the beginning looked at different models for deep generative models. We wanted to generate synthetic samples. Here, we've chosen VAE over GANs, for instance, or normalizing flows, because in VAEs we have the ways of evaluating the likelihood of the distribution we are estimating within the latent space. And this is actually very, very useful when, after in the following work, I'm estimating the risk of collision, because I want to use some quite fancy algorithm that necessitates to estimate this likelihood of the samples I'm using. So the VAE has a structure, a probabilistic structure, that is very suitable for the other algorithm I'm using for estimating the risk of collision.
thank you so much. I have another question. So you have mentioned that you compare your generative trajectory with the flight dynamics with the like
Yeah.
waypoint trajectories.
Yeah.
So have you think of how to combine the physics-based model with
Yeah,
your model?
yeah, of
Like,
course.
Is there like possibility to do this?
Yeah. That's a big question, and that's a big future work for my PhD, to try to implement those physics-based models. Unfortunately, I didn't have the time to have a look at that. But yeah, it's completely open work, and I'm not an expert in physics-based model yet, but maybe in the future I could try to work on that. We'll see.
Thank you very, very much for this very interesting talk. I only had one question. Actually, when we are controlling approach and departure, most of the time aircraft can follow the standard procedures.
Yep.
But sometimes the ATC actually changes the trajectory of the aircraft,
Yep.
like not following the standard departure. Did you take that into account in the training data that you use to then to generate the sample trajectories?
Not, well, yes and no. In the fact, of course, in the training data, we have tried to focus on trajectories that are following somehow the pre-series. But we did not completely filter the trajectory that had some ATC actions to modify this, because first, it's really hard to do that. That's one of the limitations of my work. I've presented a paper last summer actually where we had actually some problems because of those, and they completely they completely bias our probability estimation here, and so that's also one of the future work, trying to find a way to cross the data, the ADS-B data I'm using here for the trajectories, and maybe the recordings of the ATC clearances, in order to try to determine, because you have to make the difference between a trajectory that is not following the procedures because of uncertainty and a trajectory that is not following the procedures because of ATC. And this is hard, actually.
Apologies for making it even longer, but very interesting talk. So thank you for this one. Here the question would be really, when you are trying to compare those simulated trajectories with the real ones, on the side of the real ones, is there any pre-filtering? Is there any choice of the particular, let's say, Zurich Airport has a different modes, let's say different in the morning, different concepts of the flying. During the BISA you have only one runway, and so on and so forth. There will be a change of those procedures depending on the weather conditions. Is there any pre-filtering on this one when you try to do the matching?
No. The pre-filtering, of course, we pre-filtered the trajectories corresponding to the procedures we want to evaluate. So, of course, the takeoff from runway 16, and I guess runway 16 is only used in the main, how is it called?
Concept.
The main configuration at Zurich Airport, yeah. For the go-arounds, it was a bit more complex, because we don't observe that many go-arounds, and we still have to get some data to train on. And so we had to take as many go-arounds as we need. But we made some, of course, cleaning of the data. For instance, if a go-around is a bit too complex, it's going too far away, or is doing, for instance, a holding pattern or is landing on another runway, for instance, we filtered out those trajectories and we try to focus on the go-arounds that are following somehow the defined procedures in the stars or in the charts in general. Yeah.
Thank you.
Thank you very much. And